Good afternoon, students.
Good afternoon.
Good. I'm happy to be in maths class again. Are you happy to be here?
Yes, sir.
Good. Well, you know, we're on a series of sets. In our last class, what were the topics we looked at?
Symbols.
Symbols we use in sets, and then we went on to the other lesson, to the number of subsets in a given set. In this lesson, we will look at the intersection of sets. What will we look at?
Intersection of sets.
Good. So we're looking at intersection of sets. Can anybody say what you know about intersection of sets? Yes.
Intersection of sets are when two sets are combined.
When two sets are combined, it has something to do with something about combine, but you mean when both of the sets come together? Yes.
Intersection of set is when some members of the set are common.
When some members, yes. So we have something about combine, what it is when the members are common in the two sets. All right? Correct. So we can say that two sets are said to have an intersection if they have some elements in common. If they have some set of elements in common, they are said to have an intersection. So for example, if we have the set A, which is equal to 1, 3, 5, 7, 9, and we have the set B, which is equal to, let's say we have 3, 5, 6. We have the set A, which is equal to this, and the set B, which is equal to that. Well, then we can look to see whether there are any elements in common. And if there are any elements in common, we say that those elements form the set which is the intersection of these two. All right? Good. Are there any elements in common here?
Yes, sir.
You sure? What are the elements in common?
3, 5.
Correct. 3 and 5 are the elements in common. So, how do we symbolize intersection? We write A, and remember in the last class the symbol that we use for intersection. So we say A intersect B equal to, and we list the set A intersect B. And that set is 3 and 5. Lovely. Now, we can also display this on a special diagram. There's a diagram that we use when we want to show sets. It has a special name.
Venn diagram.
Venn diagram, correct. So we can display this intersection here, these sets on a Venn diagram to see when sets are intersecting what they look like. So imagine that A and B are part of a universal set. So then what we will have, let us use a rectangle to denote the universal set. And we name the universal set U. And we use two loops. One for the set A and one for the set B. And then we list the elements of A and the elements of B. But before we do that, it is best for us to list the intersection. All right? Observe that I deliberately draw these circles to be intersecting each other, so that the elements that are in common will go in the space here. All right?
Yes.
Good. So since anybody look at the diagram, they will know that, okay, these elements are both in A as well as B. So we list 3 and 5. What do we do with the other elements of A?
We put them in the set.
We put them in the set A. And what are those elements?
1, 7,
Mm-hmm.
and 9.
1, 7, and 9. And the set B?
6.
6. Any other thing? Are there any elements outside there which we can talk about? Are there any elements that we should put out here?
No.
Because we do not know what are the other elements in the universal set. All right? So we can talk about intersection, and we can represent the intersection on a diagram. So maybe we can just finish this off by slightly shading where the intersection is. All right? So this shaded region represents the intersection of the set A and B. Now, those were two sets that intersect that just had some of the elements in common. But then there are some times that the sets intersect, and sometimes all of the elements of one set can be found in the other one. So we will look at intersection of sets in the case when we have a subset. In the case when we have the subsets, let us see how these will be represented on a diagram. So if we have the set, let's say we have the set A equal to A, B, C, D, and we have the set B equal to, we have B, A, B. Then, do you agree that B is a subset of A? Yeah, B is a subset of A because all of the elements of B can be found in the set A. All right? So let us represent this on a diagram. Or first we could write B is a subset of A. Representing this on a diagram, we have a set A. And in this set A, you can find the set. We can find the set. What set is part of the set A? What set is a subset? B. So we can find the set B in this set A. What are the elements in B? A and B. And what are the elements in A that are not in B?
C and D.
We have C and we have D. Good. Now, do you agree that the intersection of A and B will be this set here?
Yes, sir.
The elements that are common, what elements are in B that are also in A?
A,
B. So the entire of B is in A. So it therefore means the intersection in this case will be this entire set here, B. So when we have one set being a subset of another set, we will say therefore that if B is a subset of A, well then B intersection A will be equal to B of itself. B intersection A will be equal to the set B of itself. Is that clear?
yes.
Sure?
Yes, sir.
All right. We looked at sets that join but just have some of the elements in common. Then we looked at sets that one set is a part of the other one, so one set is a subset of another one. Now, what about if the two sets have nothing in common? Do we have an intersection if they have nothing in common?
No, sir.
Do we have an intersection set?
No, sir.
Let us see. Let us look at intersection when the sets are disjoint. Let us look at intersection. So, if we have, for example, P is equal to the set 1, 3, 5, 7, 9, and we have Q is equal to the set 2, 4, 6, 8. We have the set P and Q. So now we're going to list the set P intersect Q. P intersect Q will therefore be equal to the set of, what are the elements we put in there? Are there any elements to go in there?
No, sir.
No. So we open these curly brackets and then we close it back to denote that there is nothing inside. All right? Yes. Where we could use the other symbol to denote the empty set. If we were to show this on the diagram, will we draw the loops to be crossing each other, intersecting each other?
No, sir.
So this is a universal set. So we can have one set, and we draw this one separate so that anyone looking at this diagram, they will see that these sets have nothing in common. So this is the set P, and this is the set Q. The elements, we list the elements 1, 3, 5, 7, 9. And we list the elements here 2, 4, 6, 8. Clear?
Yes,
Intersection of sets when they are disjoint. So when two sets are disjoint, we do not say that there is no intersection, but rather we say that the intersection is the empty set. All right? Intersection is the empty set. Good. Good. Now, let us look at some properties of intersection. Let me ask a question. If two sets intersect, let's say we have a set A and we have a set B. Do you think that A intersect B will be the same as B intersect A? All right, well, let us find that out. Whether A intersect B will be the same as B intersect A. And to find that out, we're going to use an example. So we will actually see what the intersections are. So we will look at the commutative property. We're looking at some properties of intersection, and we're going to look at the commutative property of intersection. Remember, today everything is under intersection. So we look at intersection for two sets that have some elements in common, intersection for subsets, intersection for disjoint sets. Now let us look at some properties of intersection. And the first property we will look at is the commutative property. And this says that if we have A intersection B, this will be the same as B intersection A. This is what the commutative property says, that if we have two sets that have an intersection, well then A intersect B will be the same as B intersect A. So let us say we have some set. If we're given some set, if we're given a set R, which is equal to A, B, C, D, E. This is one set R. And we have another set. We have S, which is equal to B, D, F. And we have a third set, which is T being equal to A, B, G. We have these three sets. Let us find what is R intersect S. R intersect S will be equal to what are the elements? B and D, all agree?
Yes.
B and D. What is S intersect R? S intersect R will be the elements B and D. So what we see happening here is that R intersect S refer to those elements that are in R and also in S. So the elements that are in R and also in S will be B and D. S intersect R refer to those elements that are in S and are also in R, and those elements are B and D again. So we see here that R intersect S give us the same thing as S intersect R. All right? Let us look at another property, and this property is called the associative. Associative property for intersection. And what does the associative property for intersection say? If we have let us say we have three sets. We have the sets S, R, and T. These are three sets that we have. But if we're given R is equal to the set A, B, C, D, E, this is the set R. And we have the set S, which is equal to B, D, F. We have a set T, which is equal to A, B, G. Now the question is, what is this set equal to? If we have S intersect R, we find what is S intersect R, and then we find what is the result of this intersecting T. All right, so what we want to do here is to first find what is S intersect R. So we look at S and R, and we find what that set will be. The set S intersect R, what will be those elements?
B and D.
B and D, are we sure? S intersect R, B and D, good, correct. So we want this set to intersect now, because this set here represents this part of this statement here. So we have S intersect R, which is B and D, and this must now intersect T. So we still have this as intersecting the set T. Now we see what this is equal to. What is the intersection of this set with T? So we're comparing this set and T. What are the elements in common in this set and common in there?
B.
So this is equal to B. Is A in common?
No.
G?
No, sir.
Neither D. So we have B to be in common here. So if we have S intersect R intersect T, this answer gives us B. All right? Now, the next task for us to do is to find, what about if we find R intersect T first? Come up with a set R intersect T, and then find the intersection of this set with S, and see whether it's going to be B also. All right? So if we have R intersect T, we're going to do this first, and then we're going to intersect S. And let us see what this will give us. R intersect T intersect S. Let us first look back and see what is R intersect T. R intersect T, these two sets we're looking at, what are the common elements?
A and B.
A and B. So R intersect T gives us A, B. And now we want to intersect this with S. So remember this set S here is, this set here, the intersection of R and T is AB. So we want to see what is the intersection with this and S. Let me just write back what S is right across here. So we have S is equal to B, D, F. So R intersect T intersect S will therefore be equal to this set intersect that set. All right? Which is equal to set B. So we can say, therefore, remember the previous one that we had, when we group S and R, we group S and R first, this intersection, all of this worked out to B. Now when we group R and T first, we see that the intersection worked out to B. So it therefore means we can write the conclusion that if S intersect R intersect T is equal to S intersect R intersect T. All right? So whichever one we group and we work with first, it doesn't matter. And that is what the associative law says for numbers. And we see that this associative law also applies to sets. All right? Okay, class?
Yes.
Okay, great. Yes, students. So what we will do now that we learned so many things about intersection, we're going to try an example. All right? You ready for an example?
Yes, sir.
Good. So let us try an example on intersection. So if we're given a universal set. Remember what's a universal set? What is a universal set? The set that contains everything. Good. So if we're given a universal set, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is our universal set, all numbers from 1 to 9. And then we have some subsets for this universal set. And these are the subsets. We have the subset M, which is equal to the set 2, 4, 6, 8. These are what type of numbers?
Even.
Good. We have the subset N, which is equal to 1, 3, 5, and we have 9. And then we have the set P, which is equal to 2, 3, 5, 7.
Sir, N is of 7.
Pardon me?
N, for the
odd numbers.
Well, it doesn't necessarily have to be odd numbers. All right? No, we're not, I'm not, we don't let's just say that we work with these sets here. All right? So don't worry that 7 is not there. I just wanted to point out that these are even numbers here, right? But I'm not only looking at sets of odd numbers or so. But we have this set here. So here's the work which you have to do. State which are true or false. True or false? Here are the questions for you, true or false. A, we have U, the universal set, intersect M is equal to M. You can just copy that. Then we have B, M intersect P is equal to phi, which is the null set. Think about them, don't answer us yet. We have C, the set C, which is M intersect N. M intersect N is a subset of P. Think of it, is that really true? Take another one, D. N union P is a subset of M. And lastly, when you answer these, then we're going to draw a Venn diagram to show these sets here. Anybody think they're ready to answer these questions? Are we ready? All right. You ready?
B, I suppose.
How you jump to B already? We need to start with A, right? We can't just jump to B like that, right? But we will come, when we come to B, I'm going to ask you for the answer as to whether indeed what you're saying. I remember your answer, you were saying that this is false. So remind me when we come to B, you were going to answer B. The first one, this is the universal set intersect M is equal to M. Is that true? Is M part of the universal set?
Yes, sir.
Is M a subset of the universal set?
Yes, sir.
And what did we learn about the intersection between a subset and another set? The one which is the subset will also be the intersection. So the intersection of the universal set and the set M will be M itself. Right? We can just know that by that. But then we can go back here and look. Right? What is the intersection of these two sets? We see we have 2, 4, 6, and 8. So it therefore means this entire set is the intersection of these two sets. So this first one here is true. Now we come to B. M intersect P is the empty set. You were saying it is false. M intersect P is an empty set. We're looking at M and we're looking at P. Do we have 8 in P?
No, sir.
6?
No, sir.
4? 2?
Yes, sir.
So we have at least one element, right? Yes. In the intersection. So it therefore means this intersection is not empty. This intersection has the element 2 inside. So this here is false. So B is false. What about C? M intersect N is a subset of P. This here is a subset of P. Let us see what is M intersect N. M intersect N, let us write at the corner here, M intersect N. What will this be equal to? M intersect N. Anything in here? It's an empty set. Interesting. Now, is an empty set a subset of the set P?
No, sir.
Last week we did subsets. The last session we did subsets. And we say that one set is a subset of all the other sets and that set is the empty set. So is this empty set a subset of P?
Yes, sir.
So it therefore means this statement here is true, because M intersect N is an empty set, and an empty set is a subset of P. The last one now, N union P. N union P is a subset of M. If we put together these two, and we get when we put together these two, we get 1, 2, 3, 5, 7, and 9. Are these a subset of the set M? Can all of these elements be found in M?
No, sir.
No, so then this is not a subset. What about if we had N intersect P is a subset of M? Will this be true now? Is N intersect P a subset of M?
Yes, sir.
The intersection here, is the intersection here a subset of that set? What is the intersection here?
1, 3, 5, 9, 2.
The intersection here,
3, 5,
the intersection of N and P will be 3 is common and 5. Are these elements in the set M?
No, sir.
So then this will be false. So N intersect P is not a subset of M. All right? Good. So let us go through what we have done today. We've been looking at intersection. We did intersection of any two sets, but then we look specifically at intersection of the sets when they are disjoint, when one is a subset of another one. Right? Then we look at some properties. Right? The commutative property. We look at the associative property. Good. And we did an example. To finish off this example, though, let us do a Venn diagram. All right? So we have the universal set U. Is there any intersection with M and N?
No, sir.
Is there any intersection with M and P?
Yes,
Yes,
sir.
sir.
So it means we need to join these two. All right? So we're going to join M and P. So we have M, and we join it with P. Is there any intersection with P and N?
Yes, sir.
Good. So then we join P to M. And we fill in the elements. Now, what are the intersection in M and P?
3.
M and P?
2.
2, yes. 2 was the intersection there. And P and N?
3 and 5.
Correct. 3 and 5. What are the other elements in M?
4, 6,
4, 6, 8. The other elements in P?
9.
What elements in P?
3, 7.
We already have 2, 3, and 5. So just 7 is missing. And the other elements in N will be? We have 1, 3, 5, and 9. So these are the elements. Are there any elements that are not listed here but still in the universal set? Let us see what are the elements we have here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. And what was the universal set? It was 1 all the way through to 9. Okay? So it therefore means we have answered our question for today. Good. I enjoyed working with you doing intersection of sets, and I hope you enjoy doing intersection of sets. And I will see you for the next lesson.